Bismillahirrahmanirrahim. Assalamu alaikum students. Today we are going to solve another problem. Today's problem is like this. Remember in the last lecture, in the last lecture, we calculated the uh, amounts of positive and negative charge in a copper penny. If you look or listen to that lecture, we calculated in a copper penny the magnitude of positive and negative charge, as we estimated, turned out to be 1.37 into 10 raised power 5 coulomb. Right? This was the charge we calculated in the copper penny. This much amount of positive charge it contains and this much amount of negative charge. And then we gave an estimate of the hugeness of this value when we said if we have a 100-watt 120 volt light bulb, then this much charge will flow through its filament in 38 hours. Now today's problem is in connection with this problem. I will write this way. In the problem of lecture 2, that is previous lecture, we saw that a copper penny contains both positive and negative charges, each of a magnitude 1.37 into 10 raised power 5 coulomb. Now today's question. Suppose that these charges could be concentrated, into two separate bundles held 100 meters apart. What attractive force would act on each bundle. Let me check the question before going to the solution. In the problem of lecture 2, that is previous lecture, we saw that a copper penny contains both positive and negative charges, each of a magnitude 1.37 into 10 raised by 5 coulomb. Suppose that the charges could be concentrated into two separate bundles held 100 meters apart. What attractive force would act on each bundle? As these two charges are unlike, positive and negative, there will be attractive force. Now we want to estimate that. So let us move to the solution. Simple question. So from Coulomb's law, we can find the magnitude of force. F is 1 over 4 by epsilon naught. We are assuming the charges are placed in vacuum. Q square by R square, because both charges are equal. Q1, Q2 is Q. So let us put the values. First I have 8.99 into 10 raised power 9 Newton meter square per coulomb square. This is the value of the constant. Then I have to put the value of charge 1.37 into 10 raised power 5 coulomb. Then square it. 1.37 into 10 raised power 5 coulomb. Then I square it. Then I have R, which is given 100 meter, and square it. 100 meter is the distance. 1.37 into 10 raised power 5 coulomb is the charge. Right? When you calculate this, you will get 1.69 into 10 raised power 16 Newton. That is huge. Check it at home. I mean, you need to multiply these numbers and check the value. 1.69 into 10 raised power 16 Newton. This is about, if you make another calculation, this is about 2 into 10 raised power 12 tons of force. 2 into 10 raised power 12 tons of force. Now what is ton? 1 ton, when I talk of ton of UK, there is another ton of US. We are talking in terms of ton of UK, United Kingdom. 1 ton is a unit of weight, is a unit of, I should say, mass, a unit of mass, and it is equal to UK ton is equal to 2240 pound. 2240 pound, or you can write it in kilograms. 1016.05 kg. 2240 pound, which is 1016.05 kgs. And when I say this force is about 2 into 10 raised power 12 tons of force, ton is a unit of mass, but it is force here. That means it is equal to the weight of this much mass. That means if you calculate the weight of this much mass by multiplying the acceleration due to gravity, then this will be the ratio, right? This force is about the weight of this much 2 into 10 raised by 12 tons of mass, right? You can check that. And distance of separation was only 100 meter. Now, even if the charges were separated by 1 earth diameter, that means if you increase the distance, the attractive force would still be about 120 tons. Let me write it. You can check that. Even if the charges were separated by 1 earth diameter, the attractive force would still be about 120 tons. Why we are giving this remark? Actually, we want to emphasize a fact. What fact? You can see in all of this, we have sidestepped the problem of forming each of the separated charges into a bundle. We said if these charges could be concentrated into two separate bundles, right? Whose dimensions are small compared to their separation because we assumed as if they are point charges, right? And use it the Coulomb's law in scalar form, right? But such bundles, if they could ever be formed, would be blasted apart by mutual Coulomb repulsion forces because this is a huge charge. So if you try to bundle this much charge, right, the bundle would be blasted apart by Coulomb repulsion. With this huge charge, the charge within the bundle will repel other charges in the bundle. Force will be huge, so there will be a blast. Now, the lesson of this sample problem is that you cannot disturb the electrical neutrality of ordinary matter by very much. Let me write this important conclusion. We cannot, I should say conclusion or lesson. We cannot disturb the electrical neutrality of ordinary matter very much, right? If we try to pull out any sizable fraction of the charge contained in a body, a large Coulomb force appears automatically, tending to pull it back. I repeat, if we try to pull out any sizable fraction of the charge contained in a body, for example, if we try to pull out a positive charge, the negative charge in the body will exert attractive force on that and pull it back. So we cannot disturb electrical neutrality of ordinary matter very much. This is all for today. In all these problems, there will be things to learn for you. You need to learn them, remember them, and move forward in this course. And do not forget to like and subscribe my channel. You can comment as well in the comment box. Thank you. God bless you. Assalamu alaikum.